Hello everyone, welcome to this video on some important results from matrix algebra. Uh, this section presents some selected results from matrix algebra that are particularly useful in the development and application of multivariate statistical methods. Uh, in this section, I will present some results under results and definitions, for example, under eigenvalues and eigenvectors, matrix decomposition, positive definite and positive semi-definite matrices, quadratic forms, trace results, determinant results, projection matrices, Kronecker product, and matrix differential results. So all these things will be included, especially some of the important results under these topics, which will be commonly used in multivariate statistical methods. In particular, some of these results will be used in our chapter 4, first distribution topic, multivariate normal distribution. So we start with eigenvalues and eigenvectors. Right. Let A be an n by n matrix. A scalar value lambda is called an eigenvalue of A if there exists a non-zero vector x such that Ax equal to lambda x. The non-zero vector x is called the eigenvector corresponding to the eigenvalue lambda. So that is the definition of the eigenvalue and eigenvector. So how do we usually find out eigenvalues? We consider this equation Ax equal to lambda x, which can be also written as A minus lambda times identity matrix times vector x equal to vector 0. Right. So now, in order to find out eigenvalues, we have to find out the values of lambda that satisfies uh, this equation. Now we have this system of equations here. This system of equations will have a non-zero solution for this x here. If and only if the determinant of this part, say this is like bx equal to 0, for example. So in that case, x will have a non-zero solution if and only if the determinant of b is equal to 0. So the system has non-zero solution if and only if determinant a minus lambda times I equal to 0. Right. So this is the equation that we have to solve to find out the eigenvalues. Right. Now it is a function of lambda. Right. So we have to solve this for lambda values. This equation is called the characteristic equation of A. Its solutions are the eigenvalues of A. So we have to solve that equation to get the eigenvalues. Once you have eigenvalues, then for each eigenvalue, we can find out an eigenvector x solving this equation. For each eigenvalue lambda I, solve the homogeneous system A minus lambda I times matrix I times x equal to 0. Right? So we have again the system of equations for a given lambda now. And the solution that we get for this x is that in that case is a vector. It's called the eigenvector corresponding to lambda I. A special situation occurs if this matrix A is a real symmetric matrix, eigenvectors corresponding to distinct eigenvalues are going to be orthogonal. Orthogonal means they are going to be perpendicular vectors. And also we can standardize them so that the dot product will be equal to uh, uh, when you take the square the size of that vector to be equal to 1. We can normalize it if you want, but anyway they will be orthogonal, that is perpendicular, right? The vectors that we get by solving this kind of equations, right, will be orthogonal if A is a real symmetric matrix, right? So that is a very brief uh, reminder to you about the eigenvalues and eigenvectors, right? And then quickly we will look at two types of decompositions, metric decompositions, which are useful for our multivariate normal distribution section, right? So the first one is the spectral decomposition, right? Let S be a P by P real symmetric matrix. Then S has P real eigenvalues, lambda 1 up to lambda P. But if it's a real symmetric matrix, then it has P eigenvalues and corresponding set of orthonormal eigenvectors P1 up to P, right? So orthonormal means their sizes, right? Here I mentioned the orthogonal, right? Orthonormal, once you have standardized them, they become orthonormal. So suppose the corresponding orthonormal eigenvectors are P1 up to Pp. Then for each Pi and lambda I, we can get an equation like this. S times Pi will be equal to lambda I Pi, where this Pi transpose Pj will be equal to 1 if I equal to j, otherwise it will be equal to 0. Right? So that's uh, the property of these orthonormal eigenvectors. Now let us take capital P to be the matrix of these coming from this P vectors, right? So P1 is a vector, P2 is a vector, PP is a vector, and so on. So they are eigenvectors. So the matrix, when you put those things into a matrix, then let's call it P. And let's take capital lambda to be the uh, diagonal matrix of the eigenvalues, lambda 1 up to lambda p. Then one thing we can show is that P transpose P is equal to P times P transpose equal to the identity matrix, because these P's are orthonormal vectors. And S can be represented now by writing like this. S is equal to P times this lambda times P transpose. So this representation is the one that is called the spectral decomposition of S. Right. So P is a matrix containing orthonormal eigenvectors. Lambda is the diagonal matrix uh, of eigenvalues. So then this representation is called the spectral decomposition of S. Right. We can write down this matrix notation like this also. So S is equal to sum of several matrices. Each matrix is coming from the corresponding eigenvalue and eigenvector. So lambda I times pi transpose gives you a vector. So lambda I times that one will be a vector. So when you add all those vectors, you get S. Now, this is very useful to us, especially when you want to find out the something called the square root of this matrix S, right? So if you define P times the square root of this diagonal matrix times P transpose as S square root, that is a definition, right? If you just give this label, you can easily define square root of the diagonal matrix. That is the same as the diagonal matrix of square root of uh, the eigenvalues. And all the eigenvalues in this case, we are looking at a symmetric matrix. In this case, eigenvalues are going to be positive. They are not negative, right? So therefore, this is defined. So if you consider this one and call it S half, we can show that this matrix S half times S half is equal to actually S, right? So therefore, we can call it the square root matrix of S, square root of S. So this is the uh, square root matrix of lambda. So the matrix X half is the unique, symmetric, positive, semi-definite matrix whose square is equal to S. So this is a very useful result when you are considering the multivariate normal distribution later on. So just to get an idea further, let's look at an example. So here I have a real symmetric matrix. This is real numbers and symmetric matrix. So I have used some R codes to find out the eigenvectors and eigenvalues, right? So first of all, I check whether it's real symmetric. Actually, we would have to check because you can see that it's a real symmetric matrix. So let's say E is the eigen S, right? This eigen is the function in R to find out eigenvalues and eigenvectors both. So this E will contain eigenvalues as well as eigenvectors. So let's say lambda is the diagonal values of the eigenvalues, right? E dollar values give you eigenvalues. So then let's take the matrix of uh, matrix the diagonal matrix containing those things in the diagonal. So that we get by this command diag E dollar values, we get that matrix. That is the capital lambda matrix. And then P, I put P to, I take P as the set of eigenvectors. So that's obtained by using E dollar vectors. We are extracting the components of E by putting E dollar values and E dollar vectors. So here is the diagonal matrix capital lambda when I get from the previous command, and this is the P matrix. So these are the eigenvectors. And just to check whether these are orthonormal eigenvectors, yeah, when you calculate transpose P times P, uh, you get this thing. Actually, you get some numbers, large number of decimal places. This is not exactly one, and this is not exactly zero because of the rounding of errors in the computer. But if I take the rounded value, it's completely the identity matrix. So that shows that these vectors are ortho and normal vectors. So I have now reconstruct. I see whether I can get my original matrix S by taking P times lambda times the transpose P. I calculate it. And then this is that reconstructed S. And you can see that reconstructed S is the same as our original S. So that's just a demonstration, right? Right. So now let us look at another useful decomposition that is called Cholesky decomposition. Right. Now here we are considering S to be a real symmetric positive definite matrix. In the previous situation, we didn't have that positive definite part. We considered any real symmetric matrix, but here the Cholesky decomposition can be found only if the matrix is positive definite, symmetric, real symmetric, positive definite. Then there exists a unique lower triangle matrix L with positive diagonal elements such that S is equal to L transpose. This factorization is called the Cholesky decomposition of S, and L is called the Cholesky factor of S. Okay, so let's also look at an example for this one. Here I have taken a certain matrix. It's symmetric, and we can show that it's positive definite actually, uh, uh, because we can show that it has the properties of a positive definite matrix. One way to check that is to look at the eigenvalues. Uh, if a matrix is a positive definite matrix, then all the eigenvalues must be non-negative, right? Actually, they have to be positive, right? They have to be positive. So let's look at this S matrix, and I have, yeah, you don't have to check whether it's symmetric, but I have just used is symmetric just to show that it is symmetric, because in a very large matrix, you may not be able to check each and every item to see if some matrix is symmetric, right? So you can use this command if you want to check whether a matrix is symmetric. And then I get the eigenvalues from this one, this command, values, eigen, and then extract the values. So these are the eigenvalues. They all are positive. Therefore, we can say that the matrix S that we have considered is positive definite. To obtain the Cholesky decomposition, now we have to consider, let us assume that there exists certain lower triangle matrix like this, and suppose S is equal to LL transpose. Right? Now we can find out what these constants should be by solving a system of equations. Right. So what I have to do is I have to calculate L and L transpose, right? And then LL transpose the first row, and you can equate the individual numbers, then we get this set of equations, right? Because LL dash should be equal to, first of all, first number should be 4, and like that. So L in the first one actually going to be L1 square. So therefore L11 will be equal to square root 4, that is 2. And then you have to solve system of equations one by one. You can get actually from the first one, you can get the second one. From those two, you can get the third one, and so on. You can find out all these lower triangle uh, entries of the matrix L, and I have just shown you that means you have to solve these equations, right? Then we get L to be this matrix, right? Now we can check whether you get LL dash equal to S actually. Yeah, when I do that, I get S. So that's what the Cholesky decomposition is. So here S is equal to LL transpose is the Cholesky decomposition of S. So those are two important decompositions. There are several other decompositions, but for this course, actually, for the multivariate normal distribution, only those two will be useful for us. Therefore, I restrict my discussion to only those two decompositions. Now, I have already talked about positive definite and positive semi-definite, but now I have further included few other things. Uh, 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 let A be a real symmetric n by n matrix, right? Real symmetric n by n matrix. The matrix A is said to be positive semi-definite, denoted as A greater than or equal to 0, if X transpose AX greater than or equal to 0 for every vector, every real vector uh, of n dimensional real vector, right? So when you calculate actual X transpose AX, you are going to get a constant, right? A fixed constant. That constant has to be greater than or equal to 0 for any real vector X. Then we say A is positive semi-definite, and this is the notation for that, right? This is not saying some constant is greater than or equal to 0, but we, for the matrix also, we write down like this. But this means the matrix A is positive semi-definite. So for if a matrix, a real symmetric matrix is positive semi-definite, then the following properties exist. Uh, all the eigenvalues of A are non-negative in that case. It can be zero or positive. It cannot be negative. It's non-negative. And then there exists a half matrix, square root matrix. A equals, uh, this is coming from the previous, you can see that this is coming from the previous one I showed you for a S matrix. There exists a square root. So we are considering still real symmetric situation. So therefore, for we from the spectral decomposition, we can actually get this kind of square root matrix. So there exists a square unique symmetric positive semi-definite matrix square root matrix. Uh, if you consider positive definite, in that case that equality to zero is removed, we are now considering uh, x transpose Ax to be directly positive, right? If x transpose Ax is positive for any real vector x n-dimensional, then this A matrix is called positive definite matrix. In this case, all the eigenvalues of A are positive. Earlier it was non-negative, now it's positive. We can also write down A as C transpose C for some non-negative matrix C, and we can show this result again using the spectral decomposition. And also, yeah, this is non-singular matrix, not the Cholesky one. Cholesky's one is the L is a lower triangle, but in this case, C is not necessarily a lower triangle one, but we can show this result using the spectral decomposition. And A can also be written as LL dash for a unique lower triangle. So that is coming from Cholesky's decomposition. Right. Uh, So then I present you some definition and some results for something called quadratic forms. This is also useful in multivariate analysis, especially multivariate normal distribution in our discussion about the multivariate normal distribution. What is a quadratic form? Let A be an n by n matrix and let X be an n by 1 vector. An expression of the form x transpose Ax is called a quadratic form in X. And we will denote it by Qx, Q to denote the quadratic form, and it's a function of X. So that's why we denote it by Qx. So this kind of form is called a quadratic form because if you expand this, the terms that you get have actually the power of X terms is going to be always 2. Right? We can expand this kind of matrix. Suppose A has Aij components and X has X1, X2, X3, and so on components. Then we can show this by expanding this one. Qx is equal to this expression where all the terms here are quadratic terms in terms of x's, right? So that means the power of the product, or maybe you can have xi, x1 square, x2 square, x3 square, that kind of square terms, and then all the product terms, pairwise product terms. So that's what you call a quadratic form, right? So every quadratic form can also be represented using a symmetric matrix, because x transpose Ax can be written as this, right? So that means represented doesn't mean it's equal. Quadratic form is equal to a symmetric matrix, but it can be represented using a symmetric matrix A, where A and A dash will be the same, right? So this A here can be written as, because it's symmetric, A can be written as A plus A dash divided by 2. That in that case, that will happen if only A is a symmetric matrix. Right? So that is the representation. It doesn't say that quadratic form is equal to an A, but can be represented with using a symmetric matrix. Uh, if A has a spectral decomposition, that means if A is a real symmetric matrix, then like this, for example, A is equal to P times, this is the matrix, matrix of orthonormal eigenvectors. A is the diagonal matrix of eigenvalues, and P transpose is the P transpose coming from this one. So that's what the spectral decomposition is. So if you can write down A like this, then if you define Z to be P dash X for some real uh, vector X, then X transpose AX will be equal to this thing, because you can easily show by, because this, if you substitute for A, you can get this expression, and that is equal to sum of lambda I Zi square, right? So this expression is called the canonical form of the quadratic form. Canonical form of the quadratic form, right? So Z here is P transpose X, right? So this X is coming from here, right? This the uh, the X in the original definition of the quadratic form, that X, right? So if you take Z to be P dash that X, right? So then you can write down X transpose AX, which is the quadratic form again. So the quadratic form can also be written like this. So one way to write down the quadratic form is like this. And the second time that is also equal to this expression here. And that also can be written like this. Right. Now we look at some results regarding the trace of a matrix. Trace, right? You know, trace is the sum of the diagonal values. So let A be an n by n matrix. The trace of A is the sum of its diagonal elements. Right? So trace, we write down it as TR within bracket A. That is equal to the sum of all the AI terms, I from 1 to n. Right? And then we look at some properties of this trace function. If A is an m by n matrix and B is an n by m matrix, then you can define the product of A and B. So if you look at the trace of A and B, A times B, that will be equal to trace of B times A. Right. So that will be useful sometimes. More generally, if you consider three vectors coming from this one, actually, if you consider three matrices, which can be which those metrics should have the suitable dimensions for us to consider this product here. So trace of ABC will be equal to trace of BCA, which will be the same as trace of CAB, right? So that means you can take uh, A, B, C, and then you can take B, C, and then bring A to this side, and then bring B to this side, and so on. That's what you call cyclic property. Trace has the cyclic property. You cannot interchange these numbers without the cyclic property, right? For example, trace ABC is not necessarily equal to trace BAC, right? But if you consider the change in the order of the product cyclically, then trace will be preserving, the trace will be the same. That is coming from this result. Actually, you can easily prove that. And then the next one is, if P is a non-singular matrix, then trace of P inverse AP is equal to trace of A. That again you can easily show using the circular property, right? Because it is the same as the trace of AP P inverse, and which is equal to trace of. So that's very easy. And then the next result is, if lambda 1 up to lambda n are the eigenvalues of matrix A, counted according to their algebraic multiplicities, then trace A will be equal to the sum of the lambda i's, right? So that's also a very useful result, but I'm not going to prove it. Let's just take it as it is, which will be useful. So it's uh, trace of A is equal. So this A is a n by n matrix. So trace of A will be equal to the sum of the eigenvalues. And then if you consider two vectors x and y, trace of x times y transpose. X times y transpose is actually a matrix, and that will be the same as trace of y transpose x. But in that case, y transpose x is going to be a constant. So transpose a trace of xy transpose is the same as trace of y transpose x from the result that we according to this result, right? But then y transpose x is a constant. Therefore, the trace of a constant is the same as that constant. So that's why you get this result. And in particular, if you take y transpose to be x transpose, then trace of x transpose is the same as x transpose x. Not the transpose. I'm sorry, I made a mistake. This is the trace. This is the trace. So trace of xy transpose is equal to y transpose x, and trace of x transpose is equal to x transpose x. And here is another result for trace. This is for a quadratic form, right? So for this quadratic form, x transpose ax, if you is the same as the trace of x transpose ax, and that is the same as the trace of a x transpose. You can easily again show these things uh, using the previous results that we showed, right? Now, this one comes because this is a constant anyway. So the trace of x transpose AX is the same as that value because this is a constant. So that's why this one. And this one comes from the previous result that we looked at. And then the next result, for any real matrix A, trace of A transpose A is equal to sum of all aij square terms, summation over all i's and j's. As trace of A transpose A gives you sum of all the square terms, right? Sum of the square terms of aij. Consequently, the trace of A transpose A will be always non-negative because you are adding here sum of squares. Sum of squares which has to be non-negative always. So therefore, this quantity will be always non-negative. And then some results regarding the determinant, right? For square matrices A and B of the same order, uh, determinant of A times B will be equal to the determinant of A times determinant of B. That is one result. The determinant is unchanged by the transposition. That's a very, very well-known result. I have just included just for the completion. If A is non-singular, then the determinant of A inverse is equal to 1 over the determinant of A. That's a useful result too. If P is a non-singular matrix, then the determinant of P inverse AP is equal to the determinant of A. That is, you can easily obtain this result using this result here and this result. If you combine this and this, you can easily obtain this result here. And further, if you consider some constant times A and take the determinant of that, that is equal to the constant to the power n times the determinant of A. And if lambda 1 up to lambda n are the eigenvalues of the matrix A counted according to their algebraic multiplicities, then determinant of A will be equal to the product of all the eigenvalues. So that's also a very useful result later on. Determinant of A is equal to the product of eigenvalues. If A is triangular matrix, then the determinant is the product of the diagonal elements. If it's a triangular matrix, then determinant is the product of the diagonal elements, because first of all, we take the diagonal element and then we have to subtract the values coming from the cross diagonal, but all those terms will be zero because you are the lower triangle, one triangle, lower or upper triangle values are zero. So therefore, if you have to take, when you take in the products of off diagonal values, all those will be zero. Therefore, the remaining term will be just the product of the diagonal elements. And finally, if A and D are square matrices, and if you have a block matrix like this, A, B, and 0 and D, if you consider the determinant of that block matrix, you can show that that is equal to determinant of A times determinant of D, of course, minus this thing, 0 times D will be 0. So this is a result, but this is not for individual values. These are matrices, and this result shows that the result is still valid for block matrices also, right? And then another thing called projection matrix. Projection matrix, that we can project a vector into some other vector using this kind of matrix. That's why we call it's a projection matrix. A square matrix P is called an idempotent matrix. First of all, we define idempotent matrix if P square is equal to P, right? So that's what called idempotent matrix. An idempotent matrix represents a projection. If it is also symmetric, then that means if P dash is equal to P, then P is called a orthogonal projection matrix. Right? Orthogonal projection matrix is a symmetric one. In that case, of course, idempotent matrix, of course, they are uh, we have the P square equal to P. And if it is symmetric, then it's a orthogonal projection matrix. That means in that case, the vectors of the matrix P will be perpendicular to each other. Right. If X is a matrix with full column rank, the orthogonal projection matrix onto the column space of X is defined as given by X times X transpose X inverse X transpose. That is the orthogonal projection of a matrix. Right? X is a matrix. And then if you multiply this matrix is a orthogonal projection matrix. The projection of the vector y by this px is usually denoted by y hat. And that is actually, if you remember, I know we didn't discuss this one yet. This is what you will have actually as the predicted value in the multiple linear regression. So this matrix here projects y into y hat. Right? So this is what you get as the projection matrix in that case. In the multiple linear regression, when you get the estimates using least squares method, actually this is what you call the hat matrix. In that case, hat matrix. So y hat is equal to h times y. Usually we write down that. That is also called the hat matrix in that situation. Right. The eigenvalues of an idempotent matrix are either 0 or 1. Right. So, and consequently, rank of P will be equal to the trace of P, because all the eigenvalues are going to be 0 or 1. Trace of P will be equal to some of those values, and therefore the rank will be equal to that quantity P. And then something new, very new, called Kronecker product. We are not going to use this one very much in this course, but I just include that for the completeness of the note here or the video. Uh, there is a different type of product of two matrices, right? It's called Kronecker product. Suppose A is a matrix, B is also a matrix, and then Kronecker product between A and B is defined as the a big matrix, in this case, that is coming by multiplying uh, B matrix by each of element in A, right? So A11 times B will be a matrix, and then A12 times B will be also a matrix like that. So if you put all these matrix into a big matrix, that is what you get uh, by taking the Kronecker product between A and B, Kronecker product. So if A is a M by N matrix and B is a P by Q matrix, then this will be M times P by N times Q block matrix, right? So each of these is a matrix. And then there are some results that is applicable to this new product called Kronecker product. So if you are considering some conformable matrices, that means if you in order to multiply like this, you have to have comparable dimensions, right? So if you consider that means you are considering here the usual product here, A and B between those two there is a Kronecker product, C and D between those two Kronecker product. But here this matrix, there is a block matrix time the usual matrix product. So therefore the dimension of A and B should match the dimension of C Kronecker product D, so that the usual matrix product to be meaningful, right? So that's why you mean by for conformable matrices. So in that case, we can show that this is the same as A times C. Here, A times C is the usual matrix product. A times C and then Kronecker product B times D. So that is one result. And some other important results are here. A Kronecker product B transpose is equal to A transpose Kronecker product B. That is very similar to the usual product. For the usual product, matrix product also we have this result. And then A Kronecker product B inverse is equal to A inverse Kronecker product B inverse. That is again similar to the usual matrix product. And then rank A Kronecker product B is equal to rank A times rank B, right? So those are some important results about the Kronecker product. And here are a few other. If A is n by n and B is n by m, then A Kronecker product B determinant is equal to determinant of A to the power n and determinant of B to the power n. And the trace of A Kronecker product is equal to trace of A times trace of B. If lambda is an eigenvalue of A and gamma is an eigenvalue of B, then lambda gamma is an eigenvalue of A Kronecker product B. So this, and then finally, some important results again, matrix differentiation. This may not be useful for us in this course, but later on when you look at in general multivariate analysis, this will be useful. Therefore, I included this one also here. So if you are considering for a constant vector A and some other vector x, uh, so if you consider A dash x, so this is going to be again a constant, right? Because it's going to be A1 x1 plus A2 x2 A3 x3 and so on. So when you differentiate that thing with respect to x, you are actually differentiating with respect to x1, x2, x3 individually. In that case, you will get A1, A2, A3 separately, and that will give you a vector A. right? So that is one equation. And then for a quadratic form, if you take the derivative of a quadratic form, you get a plus a dash times x as the answer, right? So here we are taking the derivative with respect to x. So here this is again a constant, right? What is a function of x? X is a vector, right? So when you are taking the derivative with respect to x, that means you are taking the derivative with respect to each component of x separately and then taking it as a uh, vector, right? So is finally going to give you a vector in this case. Uh, in particular, if A is symmetric, then A and A transpose will be the same. Therefore, this will be 2 times A in that case. And then for constant matrices A and B, now here I'm giving you the derivative with respect to a matrix X, right? So this is one useful result. Derivative of the trace of A dash X with respect to a matrix X is equal to A. And then also the derivative of the trace of X transpose AX with respect to X is equal to this expression. If A is symmetric, then of course this and these are two equal. Therefore, you can say 2A times X. Right. So that is the end of this video that presented some important results from matrix algebra, especially important for multivariate analysis. Right? In statistical multivariate analysis, these results are usually very, very useful. Some of these results will be useful for our particular course for the multivariate normal distribution as well. Right. So that is the end of this video. And the next video, in the next video, we will discuss some about some random vectors. And from there on, we will go to the multivariate normal distribution and then chi-square distribution, t distribution, and f distribution.